So if you go and look up the definition of computer science, it's the study of algorithms. How to write the steps to create our programs. It's not actually just programming. Computer science, involves programming, but once I heard this comparison, they said that astronomy is not the study of telescopes. Astronomy is the study of space, and you use a telescope to look at space. In the same way, computer science is not the study of programming. Computer science is the study of algorithms, and you use programming to implement your algorithm. It's your tool. Okay? So algorithms are really important. That's how, Google has made its billions of dollars. It wasn't on their good looks. It was on their searching algorithm. I remember when Google came out. I remember, yes, I am that old. But I remember going to my sister's work, and she worked at the Stanford Research Institute, and she said, hey, look at this new search engine. Because before Google, it was hard to find things online. Like, things weren't all connected. There was very few search engines, and the search engines that were there, they didn't work very well. And she said, look at this search engine. It works. When I search for something, it comes up. She's like, I even made it my homepage. So, that's how Google made all of its billions of dollars, by having a really good searching algorithm. It could search and read web pages on a server and then categorize them correctly because of the algorithm that they wrote. They kept this algorithm under lock and key. A lot of search engines have tried to copy them, but Google still, I would think, is probably one of the better or best searching algorithms. Okay, and they've just gotten it better and better over the years. And that's where they make a lot of their money, is being able to, they make a lot of their money through advertising and different things also, but it all started with their searching algorithm. Okay? So algorithms, I can't, express how important they are. So I gave you guys a reading here. Now, a first-level programming book doesn't go super in-depth into algorithms. They usually save a lot of the algorithm stuff for second-level programming. But I still think it's really important to understand algorithms. And so your book covers algorithms on page 34 a bit. And then it covers it more in the data structures part of your book, which we don't get to in here. So I put this reading online that you guys should read. It is from the Khan Academy. It's actually a pretty good Intro to Algorithms tutorial that you guys can read. I would have you read the first part here. All right.
What is an algorithm?
Yeah, Intro to Algorithms. And then you can move on if you want to, but the important one is probably just this first one. And they're really nice and friendly little tutorials. Okay, so they're good to look at. The binary search is a very interesting algorithm. We actually do go over this algorithm in our second level programming course and in the discrete structures class. But,
All of those are algorithms considered?
these are just very famous, easy to learn algorithms. So these are algorithms that you would learn in a second level programming course. So the part that you guys are responsible for learning is probably just this intro part. We're just doing an introduction to algorithms in this class. And the reason that I've kind of added this to this class, one, it's part of the student learning outcomes. And two, when we start getting into our harder programs, a lot of students, their hardest part is knowing where to start. They go, well, where do I start this programming problem? How do I do this? And that's your algorithm. Okay? And, I figure we go over algorithms now, and then as we get into these harder programming problems, we know where to start. We can figure out how to write them. Okay?
So an algorithm teaches you how to start the program?
No.
Or
Here, I have we're going to go through my little lecture here on algorithms. It does teach you how to start, I guess. Yes, it does. Writing an algorithm is a way to start. It teaches you how to start. And I'm just going to use, instead of formal lecture slides, I'm going to use my notes on algorithms that are part of this lab to kind of lecture on algorithms. And I gave you guys this notes. This was created by another instructor at another school, but I really like this. I think it's a good kind of, intro to algorithms. And it's how I'm going to kind of follow this methodology to write algorithms. So what is an algorithm? A recipe. Look in any of these books, any first level programming book, any kind of thing online. They usually will start this way. because people are familiar with recipes. Okay? And so a recipe is a good example of an algorithm because a recipe has a series of steps that if you follow correctly, you should get the correct result at the end. If you deviate, you won't get the correct result. Okay? And if a recipe is written correctly, a recipe is, tells you exactly what to do, how much to add exactly. It has a start, a middle, and an end of the algorithm. Okay? So a lot of times they say, okay, when you think of an algorithm, think about it in a recipe. Okay?
So it doesn't really matter which order it's in as long as...
Oh, no, it does matter. It's extremely important that our algorithm is in the correct order.
Oh,
If you follow your recipe out of order,
sorry, I don't so.
then you won't get the correct result. Okay? And so the algorithm is really a recipe, but it's a step-by-step, so a more formal explanation of what an algorithm is. It's a step-by-step instructions. Oh, here it is. A well-ordered collection of unambiguous and effectively computable operations that, when executed, produces a result and halts in a finite amount of time. And in this definition, they even underlined the very important words. It shows all the qualities of a good algorithm. Well-ordered, meaning that the order of your steps is very important. You have to follow them in that order for your algorithm to work. Okay? Unambiguous. That means there's nothing to question. When someone reads your algorithm, they know exactly what it's doing. They don't say, well, what's that variable? You didn't tell me what that variable was. Or you say, just, pour some water in a cup. Or maybe in programming, go around in a loop. Well, how many times do I loop? That would be ambiguous. If I say, iterate your loop 10 times, that's unambiguous. Okay, so unambiguous means there's no question about what you're doing. Okay. Effectively computable means that a computer can do it. Okay, it's not saying like make up a name, or you're not telling your computer like a step in your computer, go find a picture online, computer. That's not computable. A computer can't do that. Okay, you have to explain the steps to do that. Effectively computable. What's another effectively computable kind of thing? Like that all of your variables have been initialized. If you don't initialize your variables, it can't compute it correctly. Okay? So to make it effectively computable, you have to initialize and declare things. Okay? And then, when executed, produces a result and halts in a finite amount of time. That's actually important too. If our algorithm goes around and around forever and never gives us a result, it's not a good algorithm. Okay? So eventually it has to reach an end and produce a result for us. Okay? So he even went on in this document to explain. Oh, actually, here's his explanations. Okay? So well-ordered, the steps are in a clear order. Unambiguous, the operations described are understood by your computing agent, so your computer. And effectively computable, when he says computing agent, it could be a computer, but he keeps it kind of general here. They can actually carry out the operation. Okay? Because it doesn't have to be a computer. It could be a human. You could give an algorithm to a human, and then they could be your computing agent. Okay. You could have a quantum computer, which computes completely different than these computers, and that could be your computing agent. So that's why he put computing agent in there. Because other things than a computer can execute this algorithm. All right. So here's a good methodology for developing an algorithm, and we're going to follow this methodology. Okay, so step 1 is define the problem. State the problem you are trying to solve in a clear and concise terms. Now, usually the definition of our problem will come from our textbook, from the problem that he describes to us. But, we'll have to make sure that the definition is complete and clear and concise. So there's no question about what we're doing. So usually when you're defining the problem for us, it'll be me defining the problem, telling you what to do, or copying a problem from the book. List the inputs. This is important. This is how we usually start our algorithms. We'll list our inputs and our outputs. Our inputs are information we need to solve the problem, and our outputs, what the algorithm will produce as a result. That's usually where we start. We start reading, well, we read the definition, we understand the definition, then we look at our inputs, figure out what our inputs are, figure out what our output should be. Then after you figure out your input and output, you describe the steps needed to get from point A to point B, from your input to your output. Okay? And it says needed to convert or manipulate the inputs to produce the outputs, but to get from point A to point B. Okay, and later on, or not later on, down here is where we'll figure out how to do this in a formal kind of process. And then importantly, we test our algorithm. So we test it with sets, extreme values, middle values, and we've been doing that kind of pretty well. We've been testing our algorithm pretty well. Okay. All right. So we're going to kind of use this structured programming to write our algorithm. Now you'll see different types of algorithms online. There's no extremely standard way of writing an algorithm except maybe a flow chart. But we're going to use this kind of words to describe our algorithm. Okay, we'll use capital if else. We'll use capitals and we'll use these terms when describing our algorithm. Okay. So for our sequence statements, we can write it out in plain English. We'll write it out in plain English and pseudocode. For our selection statements, we'll use these. If else, and switch. We'll use our while, do while, and for. And then we'll use some pseudocode. And when we look at examples, this will make more sense. But pseudocode consists of natural language-like statements that precisely describe the steps of an algorithm or program. Plus, we can put some little programming terms, such as if I say check, or if the user input equals 5. And I could write if user input, the equal symbol 5. And that would be like pseudocode-like. Okay? In fact, let's look at our examples down here. Okay, so he gives, formal definitions there. Let's look at this example. I think looking at example really helps. All right. So here's an algorithm to get two numbers from the user, a dividend and divisor, testing to make sure that the divisor number is not 0 and displaying their quotient using pseudocode. So this is a well-written algorithm. This is what we're going to try to write for our programming problems. Okay? So notice that he has the step numbers here. And when he does a sub-step, he indents and then puts the sub-step numbers, which are part of that step. So we're going to try, we're going to do it that way. We're going to use our sub-steps and our numbering like that. We're going to use keywords like declare or prompt or get, display. We try to use these keywords that are computable by our computing agent. Okay, so we try to use those kind of adjectives. And then when we get to a branching statement, we use the capital IF, the capital do while. So we use those kind of terms. Okay. But let's read through this algorithm. So number 1, he did a declaration. And so we can make our step 1 declaration like that. He's declaring his dividend and his divisor and his quotient. We can even put what type of variable it is. So we could say declare decimal variables. Okay. And then, step 2, notice he broke it down. When you need to get user input, you have to put that as a step. So prompt the user to enter the dividend and divisor. It's its own step. You can even make a separate step to get the dividend and divisor, because that will be a separate line of code in our program. Okay. And then when we have a branching statement, you can write if, and then you can write this out in plain English if you want. Divisor is equal to 0. Sometimes I just put the equal sign and then the 0 there, but you can write it out in plain English as well. Okay. And then he has the word then, and then he has a little loop here. So he has the word do, display an error message, divisor must be non-zero, prompt the user to enter divisor and get your divisor again. And then you stay in here until they enter a divisor that's not equal to 0. Or actually, you stay in this while loop while he is equal to 0, so then you can get one that's not equal to 0. That's the only time he's going to let you leave. Remember we had that in the lab? How to keep someone there until you get the correct input. I think it was a population question in a lab. Enter a positive population. Do you remember that? Yeah. And then he likes to put his end if on its own line. Sometimes I skip that step, but okay. And then we have our display dividend and divisor. Calculate quotient as dividend divided by divisor, and then display our quotient. So notice that each step is broken down. Okay, into the small step that we can write as one programming line of code. So whenever you ever have a step, maybe you put calculate quotient as dividend divisor and show it, that would be 2 steps in one. So remember that you want to have each step so that you can translate that step to a line of code. Okay? And that would be a very well-written algorithm. All right. Let's look at flowcharts really fast here. So another way to kind of describe an algorithm is through a flowchart, and we'll be working with flowcharts more next week. Okay, we're just going to try to write them out this week, and then flowcharts are actually really easy. You only have to know a few symbols. And what's cool about flowcharts is a lot of, people out in the world maybe don't speak English or don't speak the same language, but you show them a flowchart and they understand what you're talking about. So flowcharts translate, a little bit better because they're visual tools. Okay? And so the symbols that we need to know these are our statements, or our process symbol is just a rectangle. Okay? So any kind of, if we say get user input, that would be a rectangle. Anything that in your programming, in your program ends with a semicolon, like a statement. Doing a calculation, quotient equals dividend divided by divisor would be a rectangle. Any kind of statement. When you're doing input-output, usually they do the slanted rectangle, actually. And then our decisions, this is our branching statements. So anytime you have a true or a false case, then you're going to use a diamond. We don't really use connectors all that much, but that was a connector. We can use terminals. They're the start and the stop at the end of or at the beginning and the end of our program. And then we connect our symbols with lines that tell us the flow of our program. So let's look at an example of a flowchart. And it's a flowchart of the same algorithm. Now what's important when you're doing a flowchart is that every rectangle, whether it's a slanted rectangle or a straight rectangle, will only ever have one arrow coming out of it. Okay, there's only one way that you can go in your program, coming out of a rectangle, because it's a statement, it's not a decision, so you can't have more than one arrow coming out of the rectangle. You can have more than one arrow going into a rectangle. So, like up here, maybe an example up here. In this example here, where it's showing a do while, this was the do part and this was the branching part. Notice that this arrow goes into the rectangle and the statements above go into the rectangle, so you can have more than one arrow going into a rectangle, but only one coming out ever. That's one of the #1 mistakes students make. Okay, if they have more than one. Actually, Douglas, can you get the lights? I just noticed on this recording that it will actually record the screen if the lights are off. Will you record the screen now? Maybe he won't. Oh well. We'll set the lights off. And then a diamond always has to have two lines coming out of it because you're making a decision. So if you have a diamond that only has one arrow coming out of it, then it should be a rectangle. Okay? That's probably the number one thing that students get wrong. Okay? So that's why I'm kind of emphasizing it. Rectangles, one line coming out, diamonds at least two. Now diamonds can have more than one line going to them also. So notice that our diamonds, we usually put like a Boolean statement inside of them. So this algorithm here is actually doing the same thing that that pseudocode algorithm that we just looked at was doing. It declares the variables dividend divisor and quotient. It prompts the user to enter the dividend divisor, get the dividend divisor, display your dividend divisor, and here's your branching statement. So here's when things get interesting. So your branches will always have a yes case and a no case, a true or false. You can write true or false or yes or no. And of course you would put all of your steps to your yes case and then all your steps to your no case. Now what's important here is this arrow here that leaves this box and goes back to our flow chart. If I left out this arrow, and that's another problem a lot of students make at first when they're making these flow charts, is they'll just get rid of this arrow, but what happened? It would end right here if I got rid of that arrow. So remember that you should always be able to reach the stop, no matter what path you take. So remember that you should always be able to take a path and reach your stop. That's that finite amount of time thing for algorithms. Okay? If I left out an arrow here, or you have, or if I left out this arrow and it just ended here, that wouldn't be good. I could even write a stop to here, or a line to the stop case, but they should always reach the stop case, no matter what path you take. Okay? And actually, a lot of my students do like flow charts better than the pseudocode kind of steps. Yeah, they do take a little bit longer to make, but usually they do translate better to people. But we'll work more with flow charts next week. And this didn't work. All right. And then here's some examples of how flow charts would look for these different types of statements. So here's your switch. It has a bunch of decisions moving down, the statements in your switch, and then that break statement. Cool. So I think the best way to kind of practice this, or to learn this, is to practice it. I did give you a lab on algorithms, but I'm going to give you time on Wednesday to kind of start this lab, but I put it up here anyway. And your lab this week is just to write out algorithms, just the steps. Okay, you don't actually have to implement any of them.
You mean next Wednesday?
Oh yeah, next Wednesday, sorry. Well, actually we might start it today. If we started today. Oh yeah, because today's Wednesday. I was thinking in my head it's Monday. Okay, we gotta not cut that out of the recording. That's okay. Well, I'll give you time to work on that in class. And then I gave you guys a homework problem, so I might have to adjust when that is due. So that is not due Monday. We'll make it due by next Wednesday. So that way you can start on it early. In fact, you might, when you're reading on algorithms, want to start that lab early. You might even get it done. All right. And then I gave you guys a homework problem, but that's what we're going to do today. We're going to practice writing an algorithm and implementing it for a homework, or for a problem that's similar to this, but a little bit different. And so your homework problem this week is to create this program, and then the important part of your homework this week is that you need to write the algorithm for this homework problem. So even if you write out this homework problem without writing the algorithm, I still want to see your algorithm. Hopefully you will write the algorithm first. Now a lot of my students like, some of them, not a lot of them, maybe half of them, like just to write the program and then they go back and write the algorithm after. Because for these easy problems, a lot of people can do that. Maybe you already thought how to make this program, and so you can just sit and you just write it, and then they go back and they write the algorithm after, which is not a totally bad thing to do. If you think if you want to write the program first, but make sure you write your algorithm after. It's kind of like backwards engineering. Because writing a program is creating an algorithm. When you're writing those programming steps, every line in your code is a step in your algorithm. And if you can get your code to work, you've written the algorithm. You just haven't formally written it as steps. Okay, so if you get this code to work, you can go back and write your algorithm after. Okay, but I do want to see your algorithm. Now, this kind of methodology works for a while for these easy programming problems. It's when you start getting to the really hard programming problems that you do have to write your algorithm first. In fact, one of my students, Brian Rojas, he's working with an Arduino, and he made like a puzzle box. So his puzzle box, it has he has a gyroscope in it, and so like when he moves the puzzle box a certain way, it can unlock step 1, and then you have to move it the second way to unlock step 2. And if you move it the wrong way, it resets, and then you have to go back to step 1. And he was trying to program this thing, and we definitely had to write an algorithm first, because it was a harder program to write. Okay, so when you get to those harder programming problems, you have to write those algorithms first. Okay, because that's, how you get it to work. All right? So even if you write the code first, I still want to see your algorithm. Okay? And you can do your algorithm as an attachment on a separate document. You can make a flow chart. You can just write it out in steps, or you can put it as comments in the top of your program, which I'm going to do today. We're just going to write it as comments on the top of our program, our steps. Okay, which is how a lot of students do it. All right? But your programming problem is to write a program that reads integers, finds the largest of them, and counts its occurrences. Assume that the input ends with number 0. And so if you entered 3525550, the program finds that the largest is 5 and that the occurrence count for 5 is 4. So how many times it appears in your output. Okay. He even gives you some hints in there, which I'll let you read. But this is, the hardest programming problem we have so far, so I would definitely try to write your algorithm first, okay? And then I can come around and, check to see if your algorithm's good if you want me to before you start programming, or you just start programming it. Now remember, if you program it and your algorithm isn't working, like you programmed it to your algorithm and then it doesn't work right, you can always go back and edit your algorithm, or edit your code and then edit your algorithm, okay? But your algorithm in the end should match your code when you turn this in. All right?
This is due.
When did I make this due? Yeah, we'll give a couple more days, right? Want to make it due the 11th? I think that should be pretty okay. Because we're going to do one similar today in class a little bit. All right. So I thought, for one that's similar to the one in class here, we'll program one today. We'll write out the algorithm together, and then we'll implement it. And I thought a similar programming problem would be that the user enters in a string of text, and then we count the occurrences of the letters in the text. We haven't done that one, right? Okay. Sometimes my semesters blur together. But I think that would be a similar one. Yes, we're using characters instead of numbers, but the algorithm will be very similar. Okay? All right, so let's go ahead and do this class assignment. So I do want you guys to kind of work with me. Because we are going to write out this algorithm first, and I think it's beneficial to have you guys follow along with me. So if you open up Eclipse, actually I'll just go ahead and make a new project. I'll give you guys a couple seconds to start up Eclipse. And then we're going to make a new class, and we'll name our class Count Letters because it's going to count the letters. Remember to always start your class names with a capital letter, so I put capital C for Count Letters. And then you can check mark the box public static void main string args if you want it to write it for you. You know, write that initial line of code for us, which helps us out. So this says count letters. I check marked that. I'm going to put my name and the date, which is the 2nd. And then here's where we're going to put our algorithm. So first we're going to write a description of our program so that we all know what we're doing since we didn't have a formal description from the textbook. We're going to have the user type in a sentence. And we will, or the output, the letters in that sentence. Actually, that might be kind of hard. What should we do? Have user type in a sentence. Let's just count a certain letter. Let's count the letter A, or should we count? If we count all the letters, then we kind of need an array. We're going to have to need a lot of variables. So we'll have the user type in a sentence, and we'll count the number of vowels in the sentence. And we should be familiar with that because we did that other programming problem where you guys had to see if it was a vowel or not. And then we'll output the most used vowel. So that'll be like our max vowel. So the vowel that they use the most. That we're not counting all the letters, because if we count all the letters, you really need an array, and we haven't got to arrays yet. Okay. So vowels, A, E, I, O, U, we can just count them. All right. So we have our description. The user is going to type in a sentence. We're going to count the number of vowels in the sentence, and then we'll output the most used vowel. So actually, we've already kind of taken care of a few things. But to write our algorithm in a formal way, the way that I want you guys to write it is you'll always tell me your input. So our input is a sentence from the user. And our output, what's our output? The most used vowel. Okay, so you always start with your input and output, such as if I were going to do my homework, what would be my input for this? Yeah, these integers, this list of integers. And then what would be my output? Right, good. It would be my max integer and then how many times it occurred. Okay? So that's what you would write at the top of that program. All right, so let's start with our steps. Now, step one, as we saw in the notes on algorithms, a lot of times we put our declaration, so like what we're going to declare. So we can declare a few ints to hold the count of the vowels. Now, a few ints is not very specific, so that's not a very good term to use, right? So did you see how I kind of wrote that, you know, well, what's a few ints? That leaves to question. That's not a good thing to have in an algorithm. Okay? So we should define that further. Okay? We'll say count A count D. And if we write it here, we can copy and paste this code later anyway. Or not A, sorry. A, E, I. If we have to go to another line, we can. Now mine, I have to go to another line because I have big font. What other variables do we need in our program? We need something to hold the sentence, right? So we need to hold our user input of the sentence. And then we're going to need a max variable that'll hold our max. And sometimes you just move on, and then when you think of another variable, you can stick it into step 1. Okay, so a lot of times you write your step 1, you think of some of your variables, and then you move on to your program, and then if you have to use another variable, you'll add it to the list there. Okay, so lots of times that's how I start things. Okay, what would be the first thing that you should do in your program? And typically the first thing you should do in your program is get input. Okay, so typically, you know, and we saw in that notes on algorithms, one of the first things they did, well, they declared, and then they got the input. Okay, so that's typically, you know, one of the first steps that you guys will do. You'll declare your variables, and then you'll get your input. Okay, so we could say prompt user for input. Okay, so that's a good term, prompt. He used the word get. Sorry, I couldn't remember. Okay, and then he said get the sentence and store it in the variable sentence. So notice that you can write this in plain old English. So actually, the more explanative, or the more you can explain it here, the easier it will be to write your code later. So as you're thinking of, you know, what you need to do, you can write it out in plain English, and a lot of times that helps us think how we're going to write our code. So we know we're going to get the sentence and store it in the variable sentence. Okay, obviously. And then what do we need to do? And here's where, you know, it starts getting a little bit, where you kind of have to either know programming code, or you can start writing your steps and then figure out you need to loop later. Okay. In fact, I'm just going to leave that step there. Well, maybe we could just write it this way. So let's say I didn't know I wanted to put a loop here. Okay. I kind of know that I need a loop here, but what would be my next step? Let's just think. Okay, so I have my sentence. What would be my step? So I have my sentence. What am I going to do to check the letters in my sentence? What would be my next step here? So let's say we have a sentence. Let's say our sentence is, the dog jumps over the fence. Okay, so here's my sentence. My first step would be to grab that first letter. Right? Grab a letter from my sentence. Take the first character out. Okay? So a lot of times you think about, well, let me just do my algorithm. I'll write my steps in my algorithm, then I'll think how I have to loop it. Okay? So I'm just going to leave the step numbers off, and I'm going to say get the first character from the sentence. So I'm going to take that T from my sentence. Now remember, we're just writing the algorithm, so we don't have to think about how to code it, but you want to get that T, or get that first letter from your sentence. After you get that first letter from your sentence, what do you want to do with that first letter? I only want to count vowels, so what do I need to do?
Check
Yeah, check if it's a vowel. Okay? So check if that letter is a vowel. I can even write then, because if it's a vowel, I'm going to even indent right here. Don't put my step numbers yet. Sometimes you can write it without your step numbers and put your step numbers in afterward. But I know this is going to be a sub-step because I have an if statement. So if this is true, then, and then I indent what I'm going to do if it's true. What if it's true? What am I going to do if it's a vowel? T is obviously not a vowel, but what if it was a vowel? What if I put a dog jumps over the fence? So we'll pretend it's a vowel. If he's a vowel, what do? I figure out which vowel it is and then increment that count, right? Okay. So I'm going to have some if statements in here. If the letter is an A, then increment A count. Right? And then what am I going to do next? I can even copy and paste this. If the letter is an E, then increment E count. This is going to be a long algorithm. If the letter is an I, sometimes I cheat and just put ... check all of them, but maybe we should write it out this time. Check I count. If it's an O, then you increment your O count. EIOU, and increment your U count. Now, if it's anything else, that if statement will come back as false, and we don't have to do anything, right? Now I'm going to do this for all of the letters in the sentence. So when I get to this point in my code, I can think, well, I need to come back up here. And I need to repeat this. So I know that this is going to be inside of a loop. Okay. So I can write a for statement for all of the characters in the sentence do and then I just take out the word first, because a lot of times you think about how you do it for the first one, but then you can take out that kind of terminology or wording, and then you can make these sub-steps now. And actually, since we made this a sub-step, it's going to look like this. And yes, I do want you to properly number them after. It does help. All right. So we have a branch. We have some sub-steps for in our for loop. We get the character from the sentence, check if that letter is a vowel, and then do these branching statements here. And then we'll come out of our loop. And we'll move on to step 5. And what should be our step 5? After we figure out all of our counts, actually we added a little bit more onto our algorithm. We wanted to find the max number. So I wanted to show you how to find a max. Finding a max is a very popular algorithm. You should know how to find a max in here. Okay. So to find a max, when you declare your max, you need to make your max something very, very small so that something will be bigger than him. So we'll start him out at 0 because we're going to find the max count. So we have A count, E count, I count, O count, and U count. And we want to figure out which of those is the biggest. So how do we check if A count is bigger than max? It's actually pretty easy. You just say if your A count is greater than your max, if he's greater than max, then what do I do? Then max becomes your A count. And actually we need one more variable. And max char will store the letter A. So then we know which, oops, I started putting semicolons in there, which, so we're going to need this variable max char, because if we just store the A count, whose count is that? We don't know. So we're going to have to store max char, which will store the maximum character, the character with the max count. So if you wanted to, you could declare him up here too. What do we want to do for the rest of our counts? Yeah, same thing. Actually, maybe we should just check for 2 letters. All right, so if A count, and then we have our E count. And actually, these will be step 6. And then these will be step 7. And yes, an array would have worked great right here when we do things like this. So A, E, I, and then O, and then U. All right. This is why sometimes I cheat and just put, okay, do it for all the rest of the letters. I guess since we're first learning algorithms, we will write them out. Okay. So we check, okay, if the A count is greater than max, the max becomes the A count, and our max character is A. We check the E count against max. If it's bigger than our max, then he becomes the new max. If I is bigger, then he becomes the new max. If, O and then U, same thing. And then our last step, what are we going to output? Your last step is usually an output line. You're going to output your max count and your max char. All right, so because we wrote our algorithms so very well, actually, it'll be very easy to translate it to programming code, since we did actually write up all the steps. So to translate a well-written algorithm to programming code is pretty easy, because every line inside of our algorithm is going to translate to a line of code. Okay? So when you write your algorithm pretty well, that's why I say sometimes people will just write out their code first and then come back and write their algorithm. But if you write a good algorithm, it should translate well to any, and notice that I could take this algorithm and translate it to any programming language. So when you write your algorithms, you should write them in such a way that I could go over to Maple and program it, or go over to C++ and program this, or JavaScript. Okay? So it should be pretty easy to implement now. In fact, if you want to work ahead, that's cool. But pretty much we're just going to follow our steps. So since we wrote out our algorithm, a lot of times you can copy and paste. So where it says declare a few ints and declare these things, I'm just going to Control C and copy that. And come down here in my code. I can even put a number 1 here, so this is our first step. And make sure I declare those as type integer. Since I am going to be incrementing them, it would be a good idea to initialize our counts to 0. My sentence will be a string. My max will be an integer. And my max char can be a character. So note, do that copy and paste, and then make sure you have all your variables in there. And then what's our step 2 is to get input from the user or prompt the user for input. And since every word has a vowel in it, they should enter a sentence with at least one vowel. Now I know this isn't part of our algorithm. We didn't make a keyboard object, but we do need to make a keyboard, or actually a scanner object, so we can get input from the keyboard. So that one we just kind of write. You should be getting good at this, or have some copy-paste code that you use. And you should be getting good at these errors. So remember that the scanner errors, it just needs that import statement. So remember it writes that import statement up here for us. Okay, that's our step 2. Our step 3 was get the sentence and store it in a variable called sentence. So remember, to get a sentence, you use the next line method. That's our step 3. Now our step 4 was the beginning of our loop. Remember that step 4 was a for loop for all the characters in the sentence. So we know that we're going to have a for loop. And I said for all the characters in the sentence, so actually this is a common thing to do, so I kind of know how to write this for loop. If I say I equals 0, I less than sentence dot length, I plus plus, that will iterate through all the characters in my loop. So that'll iterate the number of times as there are characters in my loop. Because sentence.length is the number of characters in the loop, and it starts at 0 because my characters start at index 0. So this goes to 0 to length minus 1. And then our step 5 was to grab that character. So get the character, get the first character, get a character from our sentence. And this one is programming language dependent. So inside of Java, the way you get a character from a sentence is to use the char method. Remember that char-at method? Remember the char-at method takes in one argument here, which is the index number of the character we're getting. And that index I will start at index 0 and go through all of the index numbers inside of our string one at a time. So this loop right here will bring each character up one at a time. Starting at index 0 for the first character, going to the last character, which is at length -1. Okay, so that's our step 5. Oh no, step 4.1. Sorry, I should have put 4.1. 4.2, check if the letter is a vowel. Now as I'm looking at my algorithm, I notice that this line is redundant because if it's an A, then it's a vowel. Okay, so maybe I want to change my algorithm. Can you change your algorithm? Yeah, you can change your algorithm. Let's say, okay, you know what? I don't like this if statement anymore because obviously if it's an A, then it's a vowel, and this if statement's not really doing anything. Yes, I'm going to get rid of him. It's really easy, so just get rid of him. And this kind of shows you that, yes, you can change your algorithm. And all you have to do is get rid of these. This is why sometimes I don't even number them till I'm all the way done. So maybe you could kind of follow that methodology in your homework. Don't bother numbering them till you're finished. Do use the indentation and then number them after. So I did step 4.1 already. Now I'll do 4.2. I'll check if the letter is an A, and if so, I'll increment my A count. All right, so this is step 4.2 to 4.6. I'm going to write it all, just copy and paste it here. So I can say an if that letter is an A, then increment my A count. Oh, count A. Sorry. I named it A count, but then up here I put count A, so I'll have to use count A. If you used A count, then use A count. If you use count A, use count A. Okay. Now notice that 4.3, my next step is to check if it's a E, and then I check if it's an I, then I check if it's an O, I check if it's an U. And you can see up here in my algorithm that they are all the same level. So then I can just copy and paste this code just like I copied and pasted my algorithm. I can check if it's an E, an I, a O, and a U. So if it's an E, I increment my E count. If it's an I increment my I count. Actually, this would have been a nice one for a switch statement, right? If it's a U, I increment my U count. Which brings up an important point. What if it is a capital? This is only checking for lowercase. So I'm going to add something in here to make it a lowercase. Okay. Wait, did I do that right? So what I did is I took my sentence and made him lowercase and then took his character. So that way I don't have to worry about the uppercase A. Otherwise I have to put an or statement in here. Looking for uppercase. And actually, to tell you the truth, we should write that in our algorithm. So if I wanted to add this in my algorithm, I would add it here. this up. Okay. Oh, I just put as a lowercase letter, so get the letter as a lowercase letter as opposed to just get the letter in my algorithm. And so remember, we have our beginning and our end of our for loop. This is getting each letter. It's incrementing those counts. And that part of our code will work. Now, before we move on to step 5, a lot of times when we get some programming code and we get some logic in here, it's a good time just to kind of stop and test it to see if things are working right at this point in our code. Okay. We kind of follow the methodology that we kind of test as we go. So if we wanted to test this code, we could test it by just printing out, oh, I keep calling him A count. So we can print out what our counts are. Now notice that we're printing out these counts outside of the for loop. So our for loop is reading in each character, checking each character, incrementing those counts. And we only want to print out the counts after we've counted all of the letters. So make sure that your output lines when you're counting things is outside of your for loop. Okay. So you can print out your other counts as well. When we get to the arrays chapter, this will be much easier to implement with arrays. So this is a good place to kind of run our code and figure out some syntax errors if we have some, or to see if we had, an error in our algorithm, which I don't think we do. So remember that I put these output lines before the end of my program, before the end of main, but outside of my for loop. And so now's a good time to kind of test and run him. You could just type in letters, or you could type in an actual sentence, but make sure you know what the output should be so that when it gives you an output, it's correct. So it should give me that I have 0 A's, that I have 1, 2, 3, 4 E's, 0 I's, 1, 2 O's, and 1 U. Cool. All right. So when you actually do test it, make sure it is giving you the correct output, which it looks like it is. Okay, so here's our for loop. Remember that our beginning and ending of our for loop starts at the beginning of our curly bracket and ends at the end of our curly bracket. And that you can name these curly brackets if you want. So sometimes, if we're not used to matching them up, or we just want to label our ending curly brackets, we can label them. And remember, if your code starts getting messy, you can do a Control-A, which selects all of your code, and a Control-I for indent, because if you keep nice, neat code, it'll be easier to debug and find your errors if you have syntax errors. Plus, it helps us read code better if we get used to reading it properly indented. Some errors that could happen: don't put any semicolons here, no semicolons here. Let's program this last part, and then we'll make sure everybody's works. And the last part relates back to your homework a lot. It's finding the max. So we want to find the max So to find the max, we have max set to 0. So max right now is set to 0, so our max right now is 0. And our max character is blank right now. Actually, we should initialize him to something. Actually, we should initialize him to something like that. Actually, we can put a white space in there. All right, so when you're finding a max, the important thing is to initialize your max to something really small. So that something will be bigger than him. Okay? And then we'll have our branching statements, and we'll say if count A is bigger than our max, then count A is the new max, right? So our max will equal count A, and our max character will equal an A. Now you can use a little copy paste because that's what we did in our algorithm. They are all kind of the similar steps. So you'll want to check your other letters. This will be our count E. And then our count I. So remember to check your count I, your max becomes your count I, and then your max character becomes an I. And then we have our count O. We're checking. And last but not least, we have our check U. If we wanted to make this run a little bit more efficiently, we can make these else ifs instead of just if statements. That way, if one of them's true, it won't execute the rest of them. That makes our code a little bit more efficient when we do things like that. Notice that it'll run the same. Oh wait, not there, sorry, up here. Not there. This one we do need an if statement because we need to check all of them against max. We could put an else if here if you wanted to modify and make it a little bit more efficient, because if he's an A, then he's not going to be an E. Though it'll run the same if you don't put the else ifs in there. Okay? Jordan, don't let them pet her when she's acting like that. She's been having problems lately. Just hook it to her leash and get her. And just pull her. Okay. All right. Now to see if this works, we do have to print it out. So it should be working. So all we need is some output lines here. And we'll say the max character is and this character appeared max times. So that was our last step. What step was that? I didn't put all of our step numbers at the end. We had our step 5 through 9, and then our last step was step 10. So these are steps 5 through 9. And then our last step was step 10. So you can type in a sentence. And you could test it. And voila, we have a great program. Sure. Up to here? And our for loop?
Yeah, well, where most of our comments are algorithm. I have to change something on mine, and all the comments that I wrote are gone.
Oh.
They disappeared.
Yes, of course. I'll post this one too. But I'm going to post it after because I do want you to turn in your guys's. So then you get credit for being here today. Actually, we're missing a lot of people today. It's kind of how I take roll. You get class points for doing this stuff.
So there's something that's not working online.
All right. Well, let me make an assignment, actually. If you got it to work, awesome, awesome. I do want you to turn it in, so we're going to make a class assignment in here. We'll call this in-class algorithms. So you get credit for working along with me today. Actually, hold on. And so we'll turn in the in-class assignment, our program, to count the vowels in a sentence. So you can turn that in-class assignment in here, just like you turn in, into Blackboard your other assignments. And I think right now is a good time for me to pause this, and we can make